Hey guys, we are currently recording. Like I said, on Friday there's going to be a test. There's going to be a test this Friday in Eduphoria. Okay. On today, I just want to talk about a few concepts involving waves that will be on the test that you guys need to know. Um, so let's start with reviewing longitudinal and transverse waves. Okay. So, okay. So, as you guys already know, um, a longitudinal wave is basically a wave that is moving uh, parallel to the direction of wave propagation. For a transverse wave is a wave that is moving perpendicular to the direction of wave propagation. And of course, we've already talked about this before. You guys can clearly see right here that this is an example of a longitudinal wave, because the guys notice the pulses. Look at the individual pulses. Okay. Notice how notice how the pulses in this medium, they are traveling from left to right. So if you guys can see that, so the pulses are traveling from left to right. Okay. But look at the individual particles, guys. So like, for example, look at one particle in this medium here, like this particle in red. Notice how this particle is also bouncing back and forward, you know, in the x direction. So it moves left, then it moves right, then it moves left, and it moves right. So in this case, the oscillation is parallel to the direction of wave propagation. But notice how that's different for the transverse wave. For the transverse wave, the oscillation is perpendicular to the direction of wave propagation. In fact, guys, look at one of these particles along this wave here. So, for example, like look at this one particle right there. Okay. Notice how that particle goes up and down along that line that I've drawn. You know, so the particles vibrate like this, whereas the wave itself is moving like this. So the point is, the oscillation is perpendicular to the direction that the wave is moving, or the direction that the wave is propagating. Okay, so this is a transverse wave. Okay. Now, there are different examples of these waves in nature. I want to start with sound waves. For those of you guys that don't know, sound is a longitudinal wave. So, guys, if you could visualize sound waves, they will look something like this. Okay, so imagine for a second that this is a speaker over here, and this speaker right here is vibrating, is pulsing. It's pulsing forward and backwards, guys. As a speaker pulses, it basically creates these pressure waves in the atmosphere, like these little dots. These little dots here. Imagine that they're air particles. And these air particles are vibrating side to side, kind of like what we see here. So, guys, imagine your eardrum is all the way on this side of the room, and there's a speaker on this side of the room. Well, it turns out, guys, the reason why you're able to hear is because what is happening is your eardrum is picking up the frequency of those particles. So those particles, as they pulse, they're basically slamming to your eardrum, and your eardrum hears that as sound. That's what sound is. Sound is nothing more but pressure waves in the atmosphere. It's a longitudinal pressure wave that looks something like this. So, guys, basically what I'm telling you guys, if I was to suck all of the air out of this room, or suck out all of the air of the room that you're in, you guys would not hear me, because without air, you can't hear sound. So if we were in outer space and there's no air in outer space, and we were yelling to the top of our lungs, you would not hear anything, because there's no air in space. There has to be air in order to hear. Okay. And by the way, guys, just so you guys know, if you guys ever heard the term pitch, you guys may have heard that term before, in like a music class or something. Pitch is equivalent to frequency. So whenever you hear sound that's at a higher pitch, that means those music notes, they're vibrating at a higher frequency. If you hear sound at a lower pitch, that means, the music, that you're listening to, or the sound that you're listening to, is playing at a lower frequency. So pitch is equivalent to frequency, just something I want you guys to keep in mind. Okay. There's one more thing that I want to talk about today before I let you guys go. And that is the speed of waves in individual mediums. By the way, guys, if you're just now coming in, if you have not filled out the attendance form, please go ahead and do so. So let me go back to my web browser. Give me just a second. Let me open up Comedy first. Okay, so while we're talking about waves, here's an important fact that I need to give to you guys, because this fact will be on the test. So here's an important fact I need to give you guys. I'm gonna write this down because this is going to be on the test this Friday. An important fact you guys need to know is that the speed of a wave stays constant as long as it's traveling through a uniform medium. The speed of a wave stays constant as long as it is traveling through a uniform medium. So here's an important fact you guys need to know. The speed of a wave stays constant as long as it's traveling through a uniform medium. So let me give you guys an example of what I mean by this. Imagine the speed of light. You guys may know that the speed of light as measured in a vacuum is 3 times 10 to the 8 meters per second. Okay, that is the highest speed in the universe. Nothing can go faster than light. But I want you guys to realize that's the speed of light that is traveling in a vacuum. In other words, that's the speed of light traveling through empty space. Believe it or not, light has a different speed if it's traveling in different mediums. So the light can be traveling through air, or it can be traveling through water. As it changes mediums, its speed changes. Okay, this is an important fact if you know. So obviously, light moves much slower in water than it does in empty space, right? Because those are different mediums. Okay? Just an important thing I need for you guys to keep in mind. And you guys, I want you guys to notice something, that this fact has important consequences. Because speed is equal to wavelength times frequency, it turns out that if you change the wavelength of a wave, you change its frequency, and vice versa. If you change its frequency, you change its wavelength. Let me show you guys an example of what I mean by this. It's better to just see this. Let me go and share my screen. So I want you guys to notice something here. I'm going to produce several waves using an electric charge. So this electric charge is vibrating and it's producing several waves. Okay, guys, I want you guys to notice what happens to the length of these waves as I increase the frequency. So notice how the wave is vibrating with a much higher frequency. But guys, look at the wavelength. Notice what happens to the length of the wave. Notice as the frequency went up, the wavelength went down. But look what happens as the frequency goes down. As I decrease the frequency, the wavelength increases. Why is this? Well, this is because of the speed of the wave staying constant in a uniform medium. So let me prove this to you guys mathematically. Imagine that I had a wave that was moving with a frequency of 2 hertz and it had a wavelength of 6 meters. Well, in this case right here, if I do 6 times 2, that means the speed is going to be 12 meters per second. Okay. But remember what I just said, guys. I just told you guys that as frequency goes up, wavelength should go down. Hopefully you guys will see why that's the case. So suppose I increase my frequency from 2 to 3 hertz. Remember, speed has to stay constant. The speed has to stay constant at 12 meters per second. Can someone tell me, if in this case right here, if the speed increases from 2 to 3, what has to happen to the wavelength? In this case right here, the wavelength decreases from 6 to what? Right? What's 3 times what gives me 12? You guys should know that. 3 times 4 gives me 12. So here's an important point I want you guys to see. Notice as I increase my frequency, I had to decrease my wavelength because the speed of a wave has to stay constant. In this case, it has to stay constant 12 meters per second. And that's what we see here. Going back to this animation, okay. Guys, going back to this animation here, you guys clearly see as I increase my frequency, notice how my wavelength decreased. My wavelength went down. Okay. So that's an important point I need for you guys to know. Okay. Any questions on those concept of waves? I just wanted to go over those concepts because they will be on the test this Friday. Any questions before I let you guys go? Any questions? Hey, like I said, I didn't want to hold class too long today. The reason why is because the Ed Puzzle video that I have posted for you guys, the Ed Puzzle video, it's about 12 minutes long. Normally, I try to keep these videos under 10 minutes, but in this case, this video here is 12 minutes. So I'm going to go ahead and release you guys earlier than normal because I want you guys to be able to watch the Ed Puzzle video and complete those questions before the end of first period. Okay. So I'm going to go ahead and make this video available for you guys. Okay, so I just published the video, so you guys should be able to see it. That is your assignment for today, is to watch the Ed Puzzle video and answer the questions in the video. In case you guys are just now coming in, let me give you guys the attendance form. Okay, the attendance form is now in the chat box. Okay, does anybody have any final questions for me before I let you guys go? So remember, guys, on this Wednesday, we're going to have a review of waves, and we're going to have a review of harmonic motion. And then on Friday, there will be the test in Eduphoria. Okay, so if you guys don't have any questions for me at the moment, you guys are free to go. Have a good day, everyone.